All right, it seems to be a pretty easy week this time. We have module 2.06, only module for the week. This one's talking a lot about significant digits, which is not too difficult of a task, but it can be a little confusing sometimes because it's hard to make sense of it. But it's here nonetheless, and I'll try my best to kind of explain how things work to you. So estimating, rounding, analyzing. Okay, so I'm going to read this to you, this example, and kind of let's make sense of it, right? So when solving most mathematical problems, it is helpful to first analyze the problem being solved. Take Philip, for example. Philip was given $100 to purchase sandwiches for a birthday party. He's going to buy 5 party sub sandwiches from the grocery store. Philip figures that sandwiches sell for $20.99. 5 subs times $20 would be right at his limit of $100. But something's wrong here, right? What's going wrong? The subs are $20.99, right? Not $20. If you bought 5 subs, he's estimating, right? He's saying about $20 per sub. 5 subs would be $100, which is his budget. But it's not really, right? Because $20.99 is really more like $21 per sub. So that's how he should have estimated it. He should have figured, oh, it's $21 per sub. That would be about $105 if I got 5 of them, which is obviously over that limit. And of course, this isn't including any tax, but if you did include tax, of course, it'd be even higher than that. So there's issues with his rounding, right? That's what we're going to try and fix today, is kind of the rounding, the estimating. First thing we're going to talk about is accuracy versus precision. A lot of times people like to think that they're the same thing, but they're not. There's a difference between being accurate and being precise. So precise is not necessarily accurate, meaning like pinpoint bullseye, but precise means that all your values are roughly about the same thing. So if you take the arrows, for example, you got the first one on top and the one below it. The one below it's more precise because all the arrows are very close together. They're grouped together. Every arrow that we shot ended up in the same place. So it's very precise. It's not very accurate because we didn't get a bullseye, but all our shots were in the same location. So all our shots can be very precise. So precision is kind of how close together they all end up being. Accuracy, however, is of course what we would assume kind of more bullseye, right? Pinpoint accuracy. So the top one, you can see those arrows are very precise because of how close they are together, but they're not very accurate because they're not really centered on the target, right? On the goal. Now the second graph, though, the one below it, it's not very precise necessarily, or it's not as precise as the top one because it's spread out, but it is more accurate because those arrows are more close to the center. They're more close to the bullseye, to the target, right? So accuracy is how close to the actual thing, but precise is just how close to each other, whether or not it's close to the target or not. So of course, if you had high precision and high accuracy, then everything's a bullseye, right? Precision because they're all grouped together, they're all very similar, and accurate because they're all on the bullseye. So that would be high precision and high accuracy. All right, so rounding, of course, can be applied many different ways. We already talked about Philip, but let's talk about the railroad for a second. The amount of rounding can affect your accuracy, of course. So for example, distance between railroad rails on the Transcontinental Railroad was set to 4.70833 feet. What would happen if the distance between rails was rounded? So if we rounded it to that's 5 decimal places that's currently written. If we rounded to 4 decimal places, it'd be 4.7083. If we rounded it to 3 decimal places, it'd be 708. If we rounded it just to 2 decimal places, it'd be 7.1. If we rounded it to 1 decimal place, it'd just be 0.7. But if we rounded it to nearest foot, it'd be 5 feet. So which one of these is right? Because they're all just the same number but rounded. So how far you round things is going to depend on your situation. And so that's what significant numbers brings us to. So that's what we're going to start talking about: significant numbers, significant figures, significant digits, whatever you want to call it. So here in this example, Sienna is measuring a rectangular canvas on which she wants to paint. One side of the canvas is 11.4 inches long and the shorter side is 8.3 inches. What is the area of the canvas? Round appropriately. So, of course, area is simple. It's just length times width, right? So we'll just do 11.4 times 8.3, right? So 11.4 times 8.3. That gets us an answer of 94.62. But we need to round our answer according to the correct number of significant digits. And so how we do that is we determine we go back to our starting values, 8.3 and 11.4, and we choose the one, surprisingly here, that has the fewest number of significant digits. So in 11.4 has 3 significant digits. It has the 1, and then the 4. 3 significant digits. Whereas the second number, 8.3, only has 2 significant digits, 8 and 3. So based on that, the fewest number of significant digits in a particular term or particular number is 2. So we want to pick the one with the fewest significant digits and then round our answer to meet that number of significant digits. So we only want our answer to have 2 significant digits in it, not 4 as it currently has. So we would round this to only 2 significant digits, which would be the first 2. So we'd round this 94, but since it's 0.62, that 94 would round up to 95. So the answer here is 95 square inches. So we don't pick the one with more significant digits. We actually pick the number with the fewest significant digits. So given that our starting numbers had 3 significant digits and 2, we picked the one with the fewest, which is 2. That means our answer should match that. Our answer should only have 2 significant digits as well. So that's how we determine how we're going to round or how far we're going to round. So, of course, we've already discussed other situations. We talked about this a little bit in a previous section, but what's the appropriate unit for specific situations? So if we're going to measure distance from your front door to your room, would you use miles? I would not use miles. If I used miles, I like how it says either your house is huge or you like really small decimals. But of course, we wouldn't use miles. We'd use feet, yards, meters, something closer to more local distance, right? What would we want to use if we were measuring the water flowing out of a fire hose? Would we want to use gallons or milliliters to describe how much water comes out of the hose? Probably gallons, right? Gallons, 100 gallons per minute from a fire hose. Milliliters are very, very tiny. So it'd be hard to really count how many milliliters come out of a fire hose. What about internet connection? Bits or megabits? Definitely megabits. If you talk about internet, any company you go to for internet speed tells you about megabits per minute, or not megabits per second. A megabit is 1 million bits. Internet's a very vast space, so megabits is the way to go. And of course, you're talking about traveling. Would you want to discuss your speed when you're traveling in a car at miles per hour or feet per second? Well, if you're running, maybe feet per second. But for a car, miles per hour. Right? So now also think about rates. So rates is something per something else. Miles per hour, feet per second, bits per second, gallons per minute, or some stuff like that, right? So what's interesting about this is the first value ends up being your dependent variable, and the second value ends up being your independent variable, meaning that gallons, the dependent variable is your y value or your y-axis, whereas the independent part ends up being your x value or x-axis. So gallons per minute, right? If you had something like that you needed to graph, the way you would do it, just knowing that your rate is gallons per minute, gallons would be the dependent variable, so it would represent the y-axis, and minutes would represent your independent variable, so they would be your x-axis. So that's kind of a neat trick to know if you're doing gallons per minute or anything like that, that the first part is your y value, which is the dependent variable, and the second piece would be your x-axis value or your independent variable. So assignments per week, if you had that on a graph, your assignments would be your y value. And your week would be your x value. okay, or your x-axis and y-axis. Same thing with calories per serving. And that's how this explains it on the graph, that the independent would be on the x, the dependent would be on the y. So Lamar is doing some research for his physical fitness class. He is looking to develop a healthy eating plan for his school's track team. What would be the best measure for the calories a person consumes? So think about a rate based on calories. Calories per what? Calories per minute? Calories per what? And the thing that makes the most sense to use would probably be calories per day. How many calories per day are we consuming? Right? That's what we want to keep track of, because that's a decent amount of time. You wouldn't want to do calories per year. That'd be way too long. You wouldn't want to do calories per minute, because there's obviously some minutes of the day where you're not consuming calories, right? So calories per day seems like a very good, appropriate measurement. So make sure that when you're doing things like this in the future, that you're using an appropriate scale, okay? Using appropriate measurements. Now let's get into some practice, right? Hillary wants to fill a mini cake pan with batter to make a mini cake for Phil's party. The cake pan is 4.0 inches long and 9.0 inches wide and 2.2 inches deep. What is the volume of the cake pan? Did I skip a page by any chance, or did I want to make sure I did that? I feel like I skipped something, but no, I guess we didn't. All right. Here's something about significant digits real quick. Let me snip this. All right. If you have a number like 70, the 0 here does not count as a significant digit, meaning that there would only be one significant digit, which is the 7. The 0 is not counting. But if the 0 is after a decimal, so for example, if you had 7.0, then the 0 counts as a significant digit. So zeros only count if they're behind a decimal, if they're in the decimal places. But zeros do not count if they're in front of decimal, unless there's another trick. Unless the zeros are sandwiched between two other significant digits. So for example, the number 701, this has 3 significant digits, because the 7 and the 1 are significant. Just simply the fact that they're not 0 makes them significant. But the 0 counts as well, since the 0 is sandwiched between them. Okay, and of course that goes for even longer numbers. So if you had 700,000 and 1, this would have 6 significant digits. The 7 and the 1 would count as a significant digit each. There's 2. But all these zeros are sandwiched between them. So since they're sandwiched between them, they all count as a significant digit as well. Okay. But if it was just 700,000 and there wasn't a 1 at the end, then this number would only have 1 significant digit, because all those zeros wouldn't count, given the fact that they are not sandwiched between anything. So zeros count if they're sandwiched between stuff, but they don't necessarily count when it's like this, 700,000. Okay. So 4.0 would have 2 significant digits in it, because the 0 comes after the decimal. 9.0 has 2 significant digits as well, for the same reason. And 2.2, of course, has 2 significant digits, simply because there are 2 numbers in it, right? 2.2, 2 significant digits. So every single number here has 2 significant digits. So when you calculate your answer, because you're doing volume, you're just going to do length times width times height. So in this case, we're going to do 4.0 times 9.0 times 2.2. And we end up with 79.2 as an answer. However, since this has 2 significant digits, that one has 2, and this one has 2, the fewest number of significant digits is obviously 2, since they're all the same. So our answer has to also have just 2 significant digits. So if we're rounding this to only 2 significant digits, because our answer currently has 3 significant digits, if we round it to only 2, then we're going to keep the first 2 and then round the last part. So to round the last part off, since it's 0.2, that would round down. So our answer would just be 79. So 79 is the answer that we would choose to appropriately round it. I know it's weird, but that's how this works. So let's try this one, right? Chance knows the length of a football field, including the end zone, is 120 yards. The width is 53.33 yards. What's the area? So 120 yards, right, times 53.33. Now notice this first number has only 2 significant digits in it because the 0 at the end doesn't count. Okay, keep that in mind. So this one only has 2 significant digits. This number has 4. So we're going to calculate the area. We're going to multiply these together. 120 times 53.33. And we end up with 6,399.6. But since the fewest, because this one has 2 significant digits, this one has 4, the fewest being 2 means that our answer should only be rounded to 2 significant digits as well. So that means rounding all the last 3 numbers off. So we round them all out. Because of where these numbers are, that 3 here is going to round up to 4. So it's going to be 6400. So 6,400 would be the appropriately rounded answer here. So the second answer. Correct. Okay? It's weird. It doesn't seem to make sense, but somehow it makes sense. Again, this one only has 2 significant digits, 6,400, because the 6-4 count, but the zeros here would not count as significant digits. So yeah, it's still 4 digits long. But of those 4 digits, only 2 of them are significant since the zeros there don't count. Okay, so I'll see if you guys want to try that one. Obviously, it'll tell you whether you get it right or wrong, so give it a go. Which rate would best measure how fast a robotic assembly line can put together tablet computers? What would be independent and dependent variable would be? So kind of curious how this one would work. How fast a robotic assembly line can put together tablet computers. So maybe like tablet computers per hour, tablet computers per minute. I don't know how fast they make tablet computers, but I would assume maybe per hour, maybe per day. I'm not a computer expert. So the preferred rate, as this one says, is tablets assembled per hour. That makes sense. So again, just kind of guessing on it, but that seems like a reasonable thing, right? Just like calories per day was reasonable earlier, but calories per year probably wasn't. So like it's, but there are other things that it could accept. You know, rates could be less preferred, like well, yeah, I mean, it's all there. So what would you do for this one? Which rate would best measure the speed of a ball falling off of a table? What would be the independent, dependent variable? By the way, the independent here, since it was tablets per hour, tablets would be the dependent, hour would be the independent, as we mentioned earlier. Because of the first part being dependent, the second part being independent. So when you have something per something, the first part is going to be the dependent part, and the second part will be the independent part. So when you have tablets per hour, that means tablets dependent, hours are independent. Just another thing to remember. This one, ball falling off a table. You could, depends on how high the table is. You could do inches per second, maybe feet per second. Something per second, I would think, would be really good for this one. So a short drop would be measured in feet per second, so that's good, or meters per second. It's probably, like I said, only a few feet away from the ground anyway. A skydiver, if you were doing a skydiver jumping instead of a ball falling, skydiver is going to fall miles throughout the sky. So miles per hour is probably good there. But yeah, you kind of have to use your own common sense a little bit to figure some of this out. What rate would best describe the distance a planet travels around in its orbit? I would probably suggest per year, maybe, because an orbit lasts 1 year. So a full orbit is 1 year for at least, Earth. Miles or kilometers per year is a good measure. So yeah, miles per year or kilometers per year. So again, it's kind of up to you to kind of use your common sense a little bit. That's pretty much it for this section, guys. It's not a very difficult section, but it can be confusing. It's very nitpicky. So you have to be really careful with how you choose things, and especially with how you round your numbers. So be careful, be mindful of that. If you have questions about significant digits, remember to just send us a message. We're happy to help you. All right. Other than that, good luck. That's it for this week. I'll see you next week. Bye.